We live in a three-dimensional world and are used to seeing the objects around us in 3 dimensions. Imagine if we were suddenly transported to a place where many of the things we are trying to identify and understand can only be viewed as 2-dimensional slices randomly cut through them. How different would our view of the world be? There is a branch of science called stereology that deals with the challenges of estimating what exists in 3 dimensions from information measured in 2 dimensions. Let's have a look at an example of these challenges. Here is a random cross-section through an object that we are all familiar with. We can see some different components denoted by the different shades of grey in the image. If we look at another random cross-section of the mystery object at the same scale, we see a different pattern of components. Any guesses yet as to what our mystery object might be? The last random section will be the best clue to the identity of the object we are looking at, the human body. Even though we are familiar with these types of images of the human body, which are slices from X-ray tomography analyses, we cannot immediately identify the 3D object that each slice represents. This illustrates the challenges in interpreting what exists in 3 dimensions when the only information you have is a 2-dimensional slice. At this point, you're probably wondering why I'm telling you this in a process mineralogy course. Because one of the challenges we face in process mineralogy is that we are trying to understand the properties of things that are solid 3-dimensional objects by measuring a 2-dimensional section randomly cut through them. For example, in optical microscopy and in MLA and QuemScan, automated mineralogy systems, we estimate 3-dimensional mineralogical characteristics from measurements on 2-dimensional polished sections. Let's have a look at an example which illustrates some of these challenges we face when measuring particle properties. Take a set of idealized particles, which are identical, all spherical, all the same diameter, all the same grade, 50% black, 50% white mineral. If we mounted the particles randomly in epoxy resin and sectioned the particles, this is what we would see in the cross-section. The first thing to notice is the size of the particle sections, which varies from the actual diameter of the spheres down to the smallest measurable size. So although we know that the spheres in our sample were mono-size, our observations in the cross-section have a distribution of sizes. What does this mean in a process mineralogy context? Well, it tells us that if we are estimating the size of objects, such as mineral grains from polished sections, we need to remember the impact of this effect, which is known as stereological error or stereological bias, on our estimate. The second difference to note is the variation in the grade of the particle sections, which ranges from 100% black to 100% white, with every possible combination of the two between. What does this mean in a process mineralogy context? This example shows that for mineral liberation measurements in polished section, the effect of stereological bias leads to overestimation of the amount of liberated mineral. The degree of stereological bias, or the level of discrepancy from actual mineral liberation, varies for different particle types. The magnitude of the bias is greatest for simple composite particle textures like those in our previous example. For complex particle textures, the liberation measured in 2D is close to the true 3D value, because wherever in the particle the section is cut, both minerals are present. And of course, a liberated particle can only be measured as liberated, and so they are not affected by stereological bias. It's important to emphasise that the presence of stereological bias does not prevent us from getting useful information from the polished sections. Since the early days of the minerals industry, engineers have successfully been using data collected from polished sections to design and troubleshoot processing plants. And not all data are affected by stereological bias. An example here being modal mineralogy data. As we saw in our earlier example with the human body, X-ray tomography offers the opportunity to analyse entire objects in 3 dimensions. In recent years, high-resolution X-ray microtomography has been applied to measure rock and mineral samples in 3D, in a way which is exactly analogous to a CAT scan of the human body. Being able to measure particles in 3 dimensions prevents stereological bias from affecting measurements of all characteristics, such as grain size and mineral liberation. Laboratory-scale X-ray tomography systems, such as the one shown here, are commercially available. These systems allow us to see mineral grains as small as approximately 1 micron inside the rock. Applications of X-ray tomography in process mineralogy are still under development, and X-ray tomography is a tool for the future rather than a current routine measurement technique. Let's have a look at how we can use the 3-dimensional imaging capabilities of X-ray tomography in a process mineralogy context. In this example, which is a 5mm particle of sulfide ore, we can see 3 distinct components and how they are arranged spatially inside the particle. These systems rely on differences in X-ray attenuation to distinguish between the components in a sample. X-ray attenuation reflects the reduction in the intensity of the X-ray beam, which occurs as a result of photoelectric absorption and scattering as it passes through the rock. In this image, the degree of X-ray attenuation at each point is represented by the grayscale value. The 3 mineral components exhibit different levels of X-ray attenuation, and this allows us to distinguish between them. An important point to note is that it is necessary to use established mineral identification techniques, for example MLA or QuemScan, to link known mineral identities with the grayscale values observed in the X-ray tomography images. In our example here, the white regions are pyrite, the light grey regions are carbonate minerals, mainly anchorite, and the dark grey regions are silicate minerals. In general, gold, platinum group minerals and many important sulfide minerals can be distinguished from one another. However, discriminating between different silicate minerals is more challenging. With continuing developments in hardware and software over the next few years, X-ray tomography has the potential to be an exciting new addition to the suite of tools available to process mineralogists. Whether we're looking for gold, base metals or iron ore, X-ray tomography brings a whole new dimension to our process mineralogy measurements. So watch this space.